The three chunks of the calculus stuff that we've started are, this is the limit calculus. This is, if you do limits, you can evaluate them graphically. That's part one. That's the first thing that we learned. We can evaluate limits also, and another way, not when we can't do graphically, when it's not convenient or not efficient or even possible. There's analytical ways to evaluate the limit. The goal is the same, is to find out the value of the limit, the output of the limit. So we'll start with graphing because it's nice to have that picture. It does give you a nice concept. And then when we do the analytic part, it's the algebraic way to do it without actually looking at the graph. Followed by, we'll do a couple derivatives, and that's a way of finding the slope of the tangent at any given x value. So that's this process you see right here. And then finally, we'll close with the area under a curve, which is really just the area between the x-axis and the graph, and where you're going to use chunky rectangles and make really poor approximations of the area like we did in class. Okay, so to the top, let's talk let's talk about limits, doing it graphically. And limit as x approaches 3. This first one is in general. There's no plus or minus, which means you need to look at coming in from both directions towards x equals 3 and tell me what the f of x or y values are doing. So if I go toward x equals 3 on the left and the right, as you approach it, they both head to the same value. They're both heading to a height of 1. So that means the limit as x approaches 3 is 1. And you have to look at both sides when it's a general limit. Number 2 is another general limit. As x approaches 1, in fact, I'll use a different color this time. I'll go red. But that's a general limit. As x approaches positive 1, you need to look at both the left and the right sides when you do that. And so the left limit goes to 1, the right limit goes to a height of 2. Those don't agree, and that's the one time a limit does not exist, is when those general limits, two sides, do not go to the same value. So your red does not exist. The limit does not exist. Then the one-sided limits are times when they have a specific plus or minus. It means from, and the positive side, the positive number side, we think of that as from the right. And it's important to use the word from. And then this next one, the negative one, I'm going to use green over here. Okay, that's a negative. That is from the left. So if you have a superscript, negative or positive, to the right of the number, it's indicating a direction you're going to come in from. Okay, now I'm going to go to the graph and talk about each of these. So from the right, now you have to read really carefully on number 3. It says x approaches negative 1 from the right side. As I approach negative 1 from the right-hand side, I'll use that same red color that I used in here. Negative 1, from the right-hand side, as it goes like this. Boom. Okay, that's it right there. So be careful that you're towards the right x value, which is negative 1, and we're coming in from the right-hand side, from the positive number side. The height of my finger is headed to a height of 1. That is the value of the limit. It's the y values that you're headed toward. The next one, the green one, as x approaches negative, this is x approaching positive 1 from the left-hand side. So there's also something to be careful of. This is a different number. This is positive 1, whereas the last one was negative 1 we were approaching. X approaches positive 1 from the left-hand side, so I'm going to go to my graph. X approaches positive 1 from the left-hand side is right here. It's already been indicated when I did the general limit around x equals 1. But I'm talking about approaching positive 1 from the left. My finger heads to a height of 1. I know there's a hole there, but that we never actually get to that hole. A limit approaches a value without actually getting there. So the hole is okay. We're not arriving at the hole. We're just indicating that the heights my finger's headed toward as I approach the value of x of 1 from the left is a height of 1. Okay, we're going to do the analytic side. So the graphical limit business is kind of nice as you approach an x value. What are your y values doing? Down here, we could graph these, but we're going to forego that and do the algebra instead that gets us the same result. It starts with, you always try and direct substitute. You try and take that limit as x approaches 0. Try and actually put 0 in for the x's and see if that works for you. The only time it doesn't work is if it causes the denominator to be 0, and that does. If I put 0 in for both of these denominator x's, I get 0 minus 0, and that is 0. That's a no dividing by 0. And we have an option to pursue. We only have a limited number of them at this point, which is good. We can factor is one option. So I have the denominator that factors, the numerator does not. Lately, our practice problems have only had numerators that factor, and it doesn't matter. Just go about some kind of simplifying. factoring if possible. And the goal is to get that x to cancel, one of these x's to cancel. So if you look closely, after factoring the denominator, I can cancel these x's. The glue is now multiplication. One of the biggest, most common mistakes on canceling is that folks forget that it cancels to 1. They also forget that there's a denominator and a numerator, and you can't switch those. This is the limit as x approaches 0 now becomes 1 over x minus 2. I'm not writing the 1 out front in the denominator there. We tend to leave that one off. But you have to remember we're canceling x over x to 1. So it's now 1 over x minus 2. We can direct substitute now. So remember in limits, we try direct substitution. Then if that doesn't work, we factor and cancel and then try direct substitution again. We always end with direct substitution, even in these analytic limits. What I get is 1 over 0 minus 2, which is 1 over negative 2, and that's negative 1/2. So that is our limit value. That means if I graphed this and I approached 0, x equals 0 from the left and the right, the height my fingers would be headed toward on the graph would be negative 1/2. So it's the value of the limit. Next one, same idea. Can we direct substitute? In this case, no. We always try that first, so always give it a shot. Dividing by 0 is a no-no, so we can't in this case. We're going to do a factoring of this polynomial. Looks like it's going to work out okay. I need the factors of 3 that add to negative 4. And the factors of 3 that add to negative 4. 3 and 1 add to positive 4, so negative 3, negative 1 is our option. And then we're going to rewrite this thing so it becomes the limit as x approaches 3 of x minus 3 times x minus 1 over x minus 3. Got them. The factors cancel, and then we're able to substitute directly after that. And that's usually the case. These are pretty nice contrived problems. Trying to keep them clean at here first. They get more complicated down the road, but not that bad. Okay, it's all about the algebra. When you're done factoring and canceling, try and direct substitute that value. 3 goes in for all the x's. 3 minus 1 is 2. And so in the end, we get the value of the limit is 2. So as x approaches 3, the height this graph would be headed to in both directions from both sides would be 2. That's the value of the limit. All right. Next piece is the derivative stuff. I'm going to make a separate video, so I'm kind of keep them separate. So you got your limits. Next I'll do a video for derivatives, and then we'll do one for the area at the end.